Hello, welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. Alright, so we are looking at MIMO channel estimation and we have looked at the statistics of the MIMO channel matrix H and the noise matrix V. Alright, so now let us derive the MMSE or the LMMSE estimate. Alright, MMSE estimate for a Gaussian prior, LMMSE estimate for any other general non-Gaussian prior of the MMSE or LMMSE estimate of the MIMO channel matrix H. Alright. So, we have the MIMO channel estimation scenario where we have Y equals X H plus V. This is your MIMO . This is your MIMO channel matrix. This is N cross R, N cross M, M cross R and N cross R. Considering IID channel coefficients, IID channel coefficients, we have shown that expected value of H transpose equals R sigma H square IID, right. IID channel coefficients with mean 0 variance sigma H square. Variance equals sigma H square each. Okay. Considering this, we have shown that it is basically expected value of the covariance, expected value of H transpose is R sigma H square times identity. Similarly, considering IID Gaussian noise samples, considering IID Gaussian noise samples Vi of k, Vi is the noise on antenna, receive antenna I, that is receive antenna I at time k. Considering IID Gaussian noise samples, mean equal to 0 and variance equal to sigma square, we have shown that the noise statistic, noise covariance expected VV transpose equal to, sorry, not 0, expected VV transpose equals R sigma square times identity matrix. Okay. So, these are the statistical properties of the channel matrix and the noise matrix, channel matrix H and the noise matrix V that we have derived in the previous module. Now, let us compute the MIMO channel matrix, estimate LMMSE estimate the MIMO channel matrix. We know from our previous discussion that the LMMSE estimate for any general parameter, the LMMSE estimate this is equal to R H Y R Y Y inverse into the observation matrix Y. Okay. So, we need to compute these quantities R Y Y, which is the covariance of Y, and R H Y, this is the cross covariance of channel matrix H comma observation vector, observation matrix Y. Okay. So, H hat we know is R H Y R Y Y inverse times Y. Okay, so let us start by computing the covariance matrix RYY. RYY, we know RYY is expected y transpose. Of course, if it is complex y, then it is y Hermitian. Let us consider, to make the scenario, consider a simple scenario. Let us start with real observation matrices y, alright, which is expected value of, now I am going to substitute, and we have done this several times before. Again it is going to be very similar, xh plus v times xh plus v transpose, which is equal to expected value of xh plus v times x plus v, xh plus v transpose is h transpose x transpose plus v transpose. This is equal to, again now taking this term, expanding this term by term, h transpose x transpose v h transpose x transpose plus x h v transpose plus v transpose, which you can simplify as, now taking this term by term, expected value of x h transpose x transpose plus expected value of v h transpose x transpose plus expected value of x h v transpose plus expected value of v transpose. Of course, now what we know, X is a deterministic matrix, a given pilot matrix. So, this can be brought out of the expectation, right. X is a fixed pilot matrix, there is nothing random about X. So, X can be brought out of the expectation operator, alright. So, X is a deterministic pilot matrix, X is a given pilot matrix, X is a given or basically a fixed pilot matrix. Hence, X can be brought out of your X can be brought out of the expectation operator. Okay. So, I can bring out X out of the expectation operator. So, bringing X out, we can write this as, now bring X out, X expected value of H transpose X transpose, we know expected value of H transpose is R sigma H square identity plus expected value of V H transpose X transpose plus expected value of, or X times expected value of H V transpose plus expected value of V transpose, and we know expected value of V transpose, this is R sigma square times identity. And now we also know that expected value of H V transpose, now we know that H is the channel matrix that arises of the environment, that is arises out of the propagation environment, and V is the noise samples, the Gaussian noise samples arising due to the thermal noise at the thermal noise at the receiver. And these two random phenomena, that is the scattering environment, the propagation environment, the signal propagation environment, and the phenomena that lead to the noise at the receiver, that is the thermal noise at the receiver, these two are independent. Hence, naturally the channel matrix H and the noise V are independent. Okay. So, we have channel matrix H comma noise V are, these are independent, because the channel matrix, this arises out of your signal propagation environment. Okay. For instance, this depends on, what does this depend on? This basically depends on the signal propagation environment depends on the number of obstructions. Is there a line of sight path or is there no line of sight path? The buildings, the trees, which are also known as the scatterers. Alright, it depends upon the signal propagation environment. Okay, the distance and the various, the locations of these scatterers, and also the delays that are introduced by the distances of these scatterers, which translate into phases, etc. Alright, and the noise V, this arises due to the this is basically the thermal noise, which arises due to thermal effects at the receiver, thermal noise at the receiver, and these two are independent. Therefore, we have the noise, the channel matrix H and noise V are independent, and therefore, we can say that since they are independent, we have expected value of H V transpose. If they are independent, that is equal to expected value of H into expected value of V transpose, and both of these are 0 means, so naturally this is equal to 0. Similarly, expected value of V times H transpose, this is also equal to 0, because the channel matrix and the noise are independent, and therefore, we have these two terms VH, expected value of VH transpose, expected value of HV transpose are 0, and therefore, what we have is that your covariance matrix RYY equals X R sigma H square X transpose plus R sigma square identity, which is basically R sigma H square X X transpose plus R sigma square identity. This is the expression for your output covariance matrix R Y Y. This is the expression for the output covariance matrix R Y Y. You can call this as star, because we will need this expression later, R Y Y. The expression of R Y Y, we are going to substitute it in the expression for the LMMSE estimate of H hat, derive the LMMSE estimate. But before that, we also need to compute the cross covariance R H Y. So, R H Y, that is given as R H Y. Again, this is similar to what we do for the multi antenna downlink channel estimation scenario, that is expected value of H into Y transpose, which is expected value of H into XH plus V transpose, expected value of H into H transpose X transpose plus V transpose, which is expected value of, well, once again you can take X outside the expectation operator, H transpose into X transpose plus expected value of H V transpose. Of course, expected value of H transpose, that we know is R sigma H square. So, this is R sigma H square X transpose, expected value of H V transpose is 0. So, this is your R H Y. R H Y is R sigma H square. So, this is again, this you can call basically your this again you can call basically your plus. So, now you can take R H Y and this star R Y Y and substitute it all the way back in this expression, that is your H hat equal to R H Y into R Y Y inverse into Y. So, what we get now, once you substitute these expressions, is basically you have H hat, the estimate of the LMSE estimate of the MIMO channel matrix the LMSE estimate of MIMO channel matrix is RHY, that is R sigma H square X transpose into RYY inverse, that is R sigma H square X transpose plus R sigma square identity inverse times your matrix times the observation matrix Y. Okay, this is what we have. And now observe that this R is a scalar quantity. So, I can bring it outside of this inverse, and when I bring it outside by this inverse, it becomes 1 over R. So, this R and R outside will cancel, and what you will have is sigma H square. Let me just write one more step. So, this is R sigma H square X transpose times, once you bring R outside, this becomes 1 over R sigma H square X transpose plus sigma square identity inverse into Y, and now you have the R and R cancel, and what you have is sigma H square X transpose sigma H square X transpose plus sigma square identity inverse into Y, and this is the expression for your LMMSE estimate of H hat. And now observe that this LMMSE estimate of H hat is identical to that of the LMMSE estimate of the downlink multi antenna channel estimation scenario, except that the vector Y bar has now been replaced by the observation matrix Y. Alright. So, the pilot matrix X is the same, and the expression in terms of the pilot matrix is the same. Alright. Simply the observation vector Y bar has been replaced by the matrix Y. Alright. So, the net what you observe is that this is similar to your multi antenna downlink channel estimation, except Y bar has been replaced by your observation vector Y bar has been replaced by Y. Okay. So, this is basically your expression for the LMMSE estimate. Of course, we can again simplify this expression. We can simplify this expression by again using the property that from your multi antenna downlink channel estimation, we know sigma H square X transpose into sigma H square X transpose times sigma H square X transpose plus sigma square identity inverse. This is equal to, well, sigma H square X transpose X plus, or sigma H square X transpose X, rather sigma H square X transpose X plus sigma square identity inverse, and therefore, employing this principle we have H hat equals, I am just going to substitute, instead of this sigma H square X transpose the first term, I am going to substitute the second term, and what I have is sigma H square into sigma H square X
transpose x plus sigma square, I am sorry, there has to be an x transpose here, sigma x sigma square I inverse x transpose y. Again you can see this x transpose x, this is a this x transpose x. Basically if you see x transpose x, this is much simpler, to compute, because x transpose x is a m cross m matrix, but x which is much smaller, but x transpose, this is n cross n matrix n, and therefore since typically n is much greater than m, typically n is much greater than m, or let us just say typically n is greater than or equal to m, therefore this it is easier to invert m cross m, easier to invert m cross m matrix. So, the second estimate, that is sigma h square times sigma h square x transpose x plus sigma square identity inverse into x transpose y, this is much more easier to compute than the first one, alright. So, this is basically the simplified expression for the LMMSE estimate of the channel matrix, MIMO channel matrix H, alright. So, we have extended this to basically MIMO channel estimation. Let us also now complete this by computing the error covariance, okay. So, one can also compute the error covariance matrix. The error covariance, that is the expected value of h hat minus h this is equal to h hat minus h into expected value of h hat minus h into h hat minus h transpose is equal to r h h minus r h y r y y inverse into r y h. I am going to substitute the different components, that is we have r h h, which is r sigma h square I minus r h y r sigma h square x transpose r y y inverse r sigma h square x x transpose plus r sigma square identity inverse times r y h, which is r sigma h square times x, okay. Now taking r outside, again bringing r outside, r becomes r inverse, bringing r outside, r becomes r inverse. So, this becomes r sigma h square I minus this r and r inverse, this cancels. So, I have sigma h square x transpose sigma h square x transpose x plus sigma square identity inverse times r sigma h square x. Now, let us take this r and r outside, then I have r sigma h square I minus sigma h square x transpose sigma h square x transpose x plus sigma square identity inverse into sigma h square x, And now you can see this part, that is sigma h square I minus sigma h square x transpose into sigma h square x transpose x plus sigma square I inverse into sigma h square x. Now this is identical to multi antenna, this is identical, you can verify this, to expression for covariance of multi antenna downlink channel estimation. Therefore, this is equal to R, this is equal to R times x transpose x divided by sigma square plus I divided by sigma h square inverse, and now take R inside, taking R inside, R becomes 1 over R, take R inside, R becomes 1 over R, and what happens is this becomes x transpose x divided by sigma square, in fact R sigma square I divided by R sigma h square inverse. This is the expression for the error covariance, expression for the error covariance of the LMMSE estimate of the MIMO channel estimation. Expression for error covariance of LMMSE estimate of MIMO channel estimation. All right. So, that is what we have. So, basically what we have done in today's module is basically we have completed this derivation for the derivation of the LMMSE estimate of the MIMO channel matrix H, also derived the expression for the error covariance of the MIMO channel matrix H. All right. In the next module, we are going to do a simple example to illustrate how to apply this. All right. So, that will basically complete this portion of LMMSE estimate, which is very important because MIMO channel estimation and MIMO channel or MIMO wireless communication is gaining prominence, is becoming it's a big part of 3G and 4G wireless communication, also moving forward in 5G wireless communication. So, MIMO channel estimation is of course one of the key components to enable MIMO wireless communication. Therefore, this process of computing the LMMSE estimate has a significant role to play in the context of wireless communication system implementation. All right. So, we will stop here and continue in subsequent modules. Thank you very much.